Hello children, today I am going to continue with the topics of moving charges and magnetism. I am going to start with some of the conceptual questions of magnetic Lorentz force. Obviously these are the questions that is usually asked in 1 year 2 marks. So I am going to start from the first question. What the first question says: a charged particle enters into a uniform magnetic field and experiences an upward force as indicated in the figure. Obviously the figure will follow. What is the charge sign on the particle? So I am going to read back. Charged particle enters into a uniform magnetic field and experiences an upward force as indicated in the figure. The question is, what is the charge sign on the particle? You can focus on the diagram. This is the given diagram for the question. I think all the three components of magnetic Lorentz force, one is magnetic field, another is velocity, another is force, you are able to see in the diagram. So let us let us represent those three sets of quantities in a coordinate frame. So you can see, so I can assume a three-dimensional frame. Say this is x-axis, y-axis and z-axis. Now I think you can focus the diagram where about the magnetic field is acting. I can assume the direction of magnetic field acts along x-axis. As per the diagram, I can assume the magnetic field is acting along x-axis. Where the force is acting, you are able to see the force vector is acting along y-axis. And where the particle is moving, you are able to see the velocity vector is acting along z-axis. This means obviously we know what is magnetic Lorentz force. F vector is q v cross b. It's q v cross b. Now obviously the direction of the force will decide the sign of the charge. The direction of the force will decide the sign of the charge or the nature of the charge. Obviously it is positive or negative, it is determined by the force direction. So obviously how to get the direction, since it is already represented in the diagram, but you know, if I am going to make a turn from V to B, so if I am going to make a turn from V to B, you just keep your fingers along the direction of V, you curl your fingers such that it moves towards B, then this will be the direction of F. So obviously it's a three-dimensional figure, so the F acts along y-axis. You are able to see F acts along y-axis. So obviously what is F is, just now we said F is equal to q v cross b. Now since this is the direction of F, obviously the nature of Q should be positive. The nature of Q should be positive. So once again I am going to read back the question. A charged particle enters into a uniform magnetic field and experiences an upward force as indicated in the figure. What is the charge sign on the particle? You can focus the diagram once again. Obviously the direction of magnetic field is along x-axis, the direction of velocity vector is along z-axis, and from the right hand thumb rule, what I can say, F is acting along y-axis. Now the direction of force only gives the nature of the charge. Since the force is acting along y and F is equal to q v cross b, so surely Q should be of positive nature. Obviously this is the first question you are going to get into the direction sense. So by getting into 2 or 3 more questions, you will be very clear to get what about the direction of all the 3 quantities. So with this I am going to get into my next question. What the next question says: a beam of alpha particle projected along positive x-axis, a beam of alpha particle projected along positive x-axis experiences a force due to a magnetic field along y-axis, What is the direction of the magnetic field? Once again, a beam of alpha particle projected along positive x-axis experiences a force due to a magnetic field along positive y-axis. What is the direction of magnetic field? Once again, what type of particle they are saying? It is alpha particle. Obviously alpha particle, they are the helium nucleus, positively charged helium nucleus. So what about the sign is a positive? What about the nature of the alpha particle? Is a positively charged particle. This is the first thing you are going to explore. Next, where the alpha particle is projected, so it is projected along x-axis, so the velocity vector is along x-axis. The velocity vector is along x-axis. Where the force acts on the charged particle, obviously it is acting along y-axis. Force acts along y-axis. So they are asking what is the direction of magnetic field? What is the direction of magnetic field? So you are able to see ultimately these two vectors, that is velocity vector and force vector, occupied x-axis and y-axis. So the only thing where the magnetic field can act is either positive z-axis or negative z-axis. So ultimately the direction rule will say whether it will be along positive z-axis or negative z-axis. So let us suppose that if I am going to assume the magnetic field is along positive z-axis, let us suppose that if the magnetic field is along positive z-axis, now if I am going to make the direction of force, you are going to keep the fingers along the direction of V and you are going to curl it, and you are able to see the magnetic field, and V orientation shows it will be inwards, yeah, downwards. What I can say, the force will be downwards, but obviously in the question where the force acts upwards. So I am going to draw this B vector in the negative z axis. I am going to draw this magnetic field in the z dash axis. Now you curl, you just keep V and V cross B, so you are able to see it is acting along y axis. So this rotation, that is V cross B, gives the direction of force. So obviously what is the direction of magnetic field is negative z axis. What is the direction of magnetic field is negative z axis. So once again I am going to read back the question. A beam of alpha particle projected along positive x-axis experiences a force due to a magnetic field along positive y-axis. What is the direction of magnetic field? Once again, where the velocity of alpha particle, it is along x-axis. Where the force acts, it is acting along positive y-axis. They are saying, they are asking what is the direction of magnetic field. So I check by putting magnetic field along positive z-axis, you are able to see it will be along y dash. If I am going to put B in z, what about the direction of force will be along y dash? But in the question the force is acting along OY, this means I have to project that magnetic field along z dash axis. So ultimately what about the direction of magnetic field is minus z axis. So I think this question will make you a better understanding about the direction of the three quantities involved in magnetic Lorentz force. So once again I am going to get back into one such similar question that will be making you much more stronger in application of the magnetic Lorentz force direction. Now what the next question says, an electron beam projected along positive x-axis, an electron beam projected along positive x-axis experiences a force, it experiences a force due to a magnetic field, it experiences a force due to a magnetic field along plus y axis. What is the direction of magnetic field? Once again, an electron beam projected along positive x-axis experiences a force due to magnetic field along positive y-axis. What is the direction of magnetic field? Now obviously here the nature of the particle is an electron, and you know it is negative. What is the nature is negative. So this is a very sensitive part. Now where the electron beam is projected, it is projected along positive x-axis. So this will be the velocity of electron, OX will be the velocity of electron. Where the force due to the magnetic field, it acts along y-axis. Now they are asking what is the direction of magnetic field. Let us assume that I am going to represent the magnetic field along z dash axis as we did in the last question. The magnetic field is acting along negative z axis. If I am going to make a turn from V to B, obviously the screw will advance along the direction of F. So if I am going to turn the fingers from V to B, it will be acting along Y, and that is the direction of force. So what is force is, you know, F is equal to QV cross B. You know, F is QV cross B. This already we did. Now, if it is positive, obviously this is very correct. But what is the nature of the charge is an electron. Since they are asking for the direction of magnetic field for the electron, you are able to see if it is a positive charge, obviously the question will be very clear. The direction of magnetic field will be along negative z axis. If it is the charge is a positive nature, what about the direction of magnetic field? It will be along z dash. But since they are asking for electron as a negative nature, so what should be the direction of magnetic field? It should be acting along positive z axis. It should be acting along positive z axis. Say if the same question is asked for a proton beam, if they are asking for a proton beam, so this question is directly obtained by this F is equal to Q V cross B, and the Z dash, that is minus Z axis, will be the direction of magnetic field. But since they are asking for electron has a negative nature, for that what about the direction will be opposite to that of this case. So I am going to get the direction along positive Z axis. So once again I am going to get back into the question. An electron beam projected along positive X axis experiences a force due to a magnetic field along positive y axis. What is the direction of magnetic field? So once again the electron is projected along OX, that is V vector, where the force acts along OY. If I am going to use the direction rule, when the screw is rotated from V to B, the screw will advance along the direction of OY as it is given in the question, and F vector, you know, it is Q V cross B. If Q is positive, obviously Z dash will be the direction of magnetic field. But since here Q is negative, since the type of particle is electron, so what should be the direction of magnetic field? It will be acting along positive Z axis. So I think with these three sets of question, now you will be in a situation to apply the direction of magnetic Lorentz force. So with this, I am going to get into my next question. What the next question says: an electric charge enters in an electric field. An electric charge enters in an electric field at right angles to the direction of electric field. What is the nature of the path followed? So once again, an electric charge enters an electric field at right angles to the direction of electric field. What is the nature of the path followed? So already in theoretical session we did an expression for the deflection of the particle when it enters the electric field, and ultimately based on that fact, what type of path is followed by the charged particle is a parabolic path. So once again, what is the path followed is a parabolic path. I think you can very easily recall the theoretical path. So when a charged particle enters an electric field, obviously the path followed by the charged particle is parabolic in nature. I am going to get into my next question. As shown in figure, a charge Q moving along the x axis with a velocity v is subjected to uniform magnetic field B acting along the z axis as it crosses the origin O. What is the first question? Trace its trajectory. Number 2, does the charge gain kinetic energy as it enters the magnetic field? You are going to justify your answer. So once again I am going to read back. As shown in figure, a charge Q moving along the x axis with a velocity v is subjected to a uniform magnetic field B acting along z axis as it crosses the origin O. Question number 1, trace its trajectory. And question number 2, does the charge gain kinetic energy as it enters the magnetic field? And you are going to justify your answer. You can focus on the diagram. You are able to see a charged particle is flowing towards the origin along x axis with a velocity vector v vector. What about the direction of magnetic field? You are able to see it is acting along z axis. So ultimately you are going to trace the trajectory. What about the shape of the path the charged particle is going to follow? So obviously let us see the diagram. You are able to see the charged particle is traveling with a velocity v vector towards the origin. It is traveling along x axis. Now once it enters, say I am going to extend this path, say once it enters this part, obviously this will be the velocity vector. What about the angle between B and V? You are able to see it is 90 degree. What about the angle between the velocity vector and the magnetic field is 90 degree. This means V and B are perpendicular. V and B are perpendicular, and already we discussed when the velocity vector and the magnetic field vector are perpendicular, the charged particle experiences a centripetal force, and as a consequence it moves in a circular path. So obviously as it enters at this point, obviously the charged particle will follow a circular path like this. So obviously this is the trajectory. This is the trajectory. Now, what is the second question they are asking? Does the charge gain kinetic energy as it enters the magnetic field? Obviously, this is a very important question. When the charge enters the magnetic field, they are asking, does the charge gains kinetic energy? And if yes or no, you are going to justify your answer. So let us explore once again. So when V and B are perpendicular, obviously the charge experiences a centripetal force, and as such it moves in a circular path. So the trajectory is a circular path. But already we studied, what about the magnetic Lorentz force? It does no work on the charged particle, as force and the motion are perpendicular. You are able to see the force and the motion of the charged particle are perpendicular. Obviously the magnetic Lorentz force does no work on the charged particle. If this means if there is no work, then there is no change in the magnitude of the velocity. This we studied already. Once again, since the magnetic Lorentz force does no work on the charged particle, since the force and the velocity vector are perpendicular, so ultimately what we are going to say, no work is done by the magnetic Lorentz force on the charged particle, and as such we can conclude that there is no change in magnitude of the velocity. And if ultimately the velocity is not going to change, the magnitude of the velocity is not going to change, obviously the kinetic energy remains unchanged. So once again, what the question says, does the charge gain kinetic energy? The answer is no. Since there is no change in the magnitude of the velocity, what is the reason? Since the force and motion are perpendicular, the magnetic Lorentz force does not perform any work on the charged particle, and ultimately there is no change in the magnitude of the velocity, and ultimately what is the conclusion? There is no change in velocity, there is no change in kinetic energy. So once again, I am going to read back the question. As shown in figure, a charge q moving along the x-axis with a velocity v is subjected to a uniform magnetic field acting along z-axis as it crosses the origin O. You are going to trace its trajectory. And number 2, does the charge gain kinetic energy as it enters the magnetic field? Justify your answer. So once again, the diagram clearly says the charge is traveling along x-axis, and it enters at this point, and it enters along OX dash axis. Obviously it enters along OX dash axis. So you are able to see the velocity vector and the magnetic field vector are perpendicular. So when V and B are perpendicular, you know, obviously this is the case of centripetal force, and the charged particle traces a circular path as shown. Now the second question is there any gain in kinetic energy by the charged particle? The answer is no. What is the reason? Since the force and the motion are perpendicular, the work done by the Lorentz force on the charged particle is 0. So no work is done by the magnetic Lorentz force on the charged particle. This means there is no change in the magnitude of the velocity of the charged particle, and if there is no change in the magnitude of the velocity, ultimately there will be no gain in kinetic energy of the charged particle. So obviously this is one of the most important question that has a good concept of magnetic Lorentz force. So with this I am going to get into my next question. What the next question says, in a certain arrangement a proton does not get deflected. In a certain arrangement a proton does not get deflected. A proton does not get deflected while passing through a magnetic field region. While passing through a magnetic field region. Now the question is, under what condition is it possible? Under what condition is it possible? So once again I am going to read back. In a certain arrangement, a proton does not get deflected while passing through a magnetic field region. Under what condition is it possible? So I think we can start from the magnetic Lorentz force. You know, F is equal to Q V cross B, and you know, in magnitude form, if I am going to write it as BQV sine theta, theta will decide F. Now you are able to see they are giving a situation in which the proton is not at all deflected. This means no force is acting. There is no deflection means no force is acting on the proton. So what type of orientation, what type of motion of that proton will lead to zero force? Obviously it's a very clear cut. We studied all those cases. So by setting theta equal to 0, by putting theta equal to 0, F will be 0. This means when the charged particle is moving parallel to the direction of magnetic field, this means when the proton, obviously the charge is proton, so when the proton is traveling along the direction of magnetic field, or I can say it is traveling parallel to the direction of magnetic field, the force experienced is 0, or I can say it does not get deflected while passing through the magnetic field region. So once again the question is, in a certain arrangement, a proton does not get deflected while passing through a magnetic field region. Under what condition is it possible? So once again the question is, they are saying the F is 0. Obviously the undeflected case means the force on the proton should be 0, and under what condition it will be? When the charged particle or the proton is moving parallel to the direction of magnetic field. So I am going to get into my next question. What the next question says, in a certain arrangement, a proton experiences maximum force. In a certain arrangement, a proton experiences maximum force while passing through a magnetic field region. Under what condition is it possible? So once again it is the second set of question. I am going to repeat it back. In a certain arrangement, a proton experiences maximum force while passing through a magnetic field region. Under what condition is it possible? So obviously it is a reverse of the last question. Here they are asking, what about the orientation of the proton with respect to the magnetic field which results in maximum force? So obviously I am going to get back into the same expression. What is magnetic Lorentz force? F vector is equal to Q V cross B. In magnitude form I am writing F is equal to BQV sin theta. So I said theta will decide. So when theta is maximum, 90 degree. When theta is maximum for sine 90 is 1. For sine angle, theta is maximum for 90. So sine 90 is 1. So this will be the maximum force experienced by the proton. So what is the conclusion I can say? When the charged particle is moving perpendicular to the magnetic field, the force experienced by the charged particle is maximum. So once again I am going to read back the question. In a certain arrangement, a proton experiences maximum force while passing through a magnetic field region. Under what condition is it possible? So once again, when the charged particle is moving perpendicular to the direction of magnetic field, the force experienced by the charged particle will be maximum, and as by setting sin theta, theta is 90, sin 90 is 1, that will be the maximum Lorentz force acting on the proton. So with this I am going to get into my next question. What the next question says, two protons P and Q, moving with the same speed, they are moving with the same speed, enters magnetic field B1 and B2, at right angles to the field direction. Obviously the orientation is perpendicular. If B2 is greater than B1, for which of the proton P and Q, the circular path in the magnetic field will have a smaller radius. So once again I am going to read it back. Two protons P and Q moving with the same speed enters magnetic field B1 and B2 at right angles to the field direction. If B2 is greater than B1, for which of the protons P and Q, the circular path in the magnetic field will have a smaller radius. So obviously there are two protons B and Q, their speeds are same. What about the magnetic field? They are entering at right angles to a magnetic field. P enters B1, Q enters B2. What about the magnitude? B2 is greater than B1. So obviously when a charged particle enters perpendicular to the direction of magnetic field, obviously it follows a circular path. They are asking which will have a smaller radius, which proton will cover a smaller radius. So for this you should know what about the expression for the radius of the circular path covered by the charged particle. I think you can easily recall R is equal to mv by bq. This we derived. R is equal to mv by bq. Now obviously they are asking the radius. Since v is same, m and q are same, so directly we can establish, since v is same, mass of proton is same, charge is same, so directly I can write R is inversely proportional to the magnetic field. R is inversely proportional to the magnetic field. They are asking for smaller radius. This means the proton which will have larger magnetic field will have a smaller radius. Since R is inversely proportional to B, I am going to say the proton with larger magnitude, the proton that enters a larger value of magnetic field will have a smaller radius. So obviously from this data, Q will have a smaller radius. Q will have a smaller radius. Obviously this is also one of the most important questions that is usually repeated in the examination paper. So I am going to read it back. Two protons P and Q moving with the same speed enter magnetic fields B1 and B2 respectively at right angles to the field directions. If B2 is greater than B1, for which of the protons P and Q, the circular path in the magnetic field will have a smaller radius. So once again, two protons P and Q, they are entering with same speed in magnetic fields B1 and B2. B1 is for P, B2 is for Q. How the orientation is? They are entering at right angle. This means the velocity vector and the magnetic field vector are perpendicular. So what is the case we studied? When V and B are perpendicular, the type of path followed is a circular path due to the gain in the centripetal force. And what about the radius of the circular path? You know, R is equal to mv by bq. Since it's the proton, mass of the two proton is same, charge is same, V already they are saying same. So by establishing a relation, R is proportional to 1 by B. So what I can say, the radius of the circular path covered by the protons will be inversely depending on the strength of the magnetic field. Based on this fact, what the question they are asking is, which proton will cover a circular path with smaller radius? Now, since V2 is greater, since the magnetic field for Q is greater, so Q will cover a smaller radius of circular path. So I think this is much clear to you. I am going to get into my next question. What the next question says? Next question is also a very important one. A point charge plus Q, is moving with a speed V. A point charge plus Q is moving with a speed V perpendicular to a magnetic field B as shown in figure. Perpendicular to a magnetic field B as shown in figure. Explain what should be the magnitude and direction of the applied electric field so that the net force acting on the charge is 0. So I am going to read it back. A point charge plus Q is moving with a speed V perpendicular to a magnetic field B as shown in figure. Explain what should be the magnitude and direction of the applied electric field so that the net force acting on the charge is 0. Where the charge particle is moving, you are able to see the charge particle is moving along the positive x-axis. So obviously this is the velocity vector. Since you are able to see very clearly where the magnetic field is acting, the magnetic field is acting inwards. You are able to see, since it's a cross representation, the magnetic field acts inwards. Obviously this is Q. Now what about the direction of magnetic Lorentz force? Obviously what I said, you just keep your fingers in the direction of V, curl your fingers so that it moves to B. This thumb will indicate the direction of force. Obviously it will be three-dimensional figure, so it will be acting along OY. It will be acting along OY. So OY is the magnetic Lorentz force. Now the question is, they are asking what should be the magnitude and direction of the electric field so that the net force on the charge should be 0. So already the charge is under the action of magnetic Lorentz force, where the magnetic Lorentz force acts along OY. So the magnetic Lorentz force acts along OY, and magnitude wise the magnetic Lorentz force I can write BQV. since it is perpendicular, sin theta is sin 90. So where the magnetic Lorentz force acts along OY, so the magnitude wise magnetic Lorentz force is BQB. For the charged particle to remain undeflected, obviously there should be an electric field opposite to that. Obviously the electric field should act along YO. The electric field should be acting along the direction YO. Now what I can say, what is the magnitude of the electric field? You know, QE should be equal and opposite to BQV. We are able to see QQ cancel. What about the expression for electric field is BV. So once again they are asking what should be the magnitude and direction of the electric field so that the charge remains undeflected. For this, the force due to the electric field should be equal and opposite due to the magnetic field, force due to the magnetic field. So ultimately on neutralization I am getting E is equal to BV, and this is the strength of magnetic field. With this I am going to end my session. Take care of yourself.